Stereo isomerism is a branch of isomerism that studies the arrangement of atoms in space. In other words, the spatial arrangement of atoms. Now we have two major types of stereo isomerism. We have the geometric and we have the optical. Now I want to start with the optical first, and then later we'll look at geometric later. So I want to start with optical. Okay. So let's look at what optical isomerism is and how we can solve questions regarding optical isomerism. Optical isomerism is exhibited. Optical isomerism is exhibited by compounds. It's exhibited by compounds that are optically active. They are exhibited by compounds that are optically active. They are exhibited by compounds that are optically active. Now, as the name implies, optical. Optical is obtained from the word optics. And in physics, optics means light. So apparently, any compound that exhibits optical isomerism must actually be able to rotate plane polarized light. But that's not basically what we want to be looking at. Now, under optical isomerism, what are the things you need to look out for? The first one is, so under optical isomerism, I just had to outline what we need to actually understand, so that if you're studying, you don't have to go through the stress of flipping your textbook left, right, center. Once you understand these three guys, it's definitely going to help us understand much better. The first one is that types of compound that exhibit optical isomerism. Those types of compound are called chiral molecules. And for a compound to be called a chiral molecule, there must be a criteria. There must be a criteria that every compound must possess if they are to be called chiral molecules. And that criteria is what we're going to be talking about. Now, after this guy, we now look at the enantiomer, methyl compound, and the rest of them. So I have to make it this way so that once we're able to cover this, we're at least 85 to 90% good with regards to optical isomerism. So let's look at the first one. Please put down. Please put down paragraph. The type of compound that exhibits optical isomerism are called chiral molecules. Are called chiral molecules or optical isomers. Types of. Now look at what are the criteria. What are the criteria that a particular compound must possess before it can be called a chiral molecule? Please put down. The criteria that a particular compound must possess in order to be called a chiral molecule is that they must contain a chiral carbon. They must contain a chiral carbon. They must contain a chiral carbon. Okay, let me get that. All right. Now this is number one criteria. All right. For any compound to be called chiral molecule, they must contain chiral carbon. Now, what is a chiral carbon? You may want to ask. Please put down. A chiral carbon is a carbon atom that has 4 different substituents or attachments. It's a carbon atom that has 4 different substituents or attachments. A chiral carbon is a carbon atom that has 4 different substituents or attachments. So, please note that chiral carbon can also be called asymmetry. Can also be called asymmetry. Now, what do we mean? Let's look at an example of a chiral carbon. Let's put C here at the center. We have this, 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 and we have this. If here has H, and here has CH3, and here has OH, and this guy has CH3, CH2. Now this carbon atom here is a chiral carbon. It is a chiral carbon. Why? Because there is a presence of a chiral, it's a chiral molecule, but there's a presence of a chiral carbon here. Please, once they give you a compound, maybe after now we're going to look at various ways questions could be asked under this. Because they can give you a compound and they say, which of the following are chiral molecules? They'll give you the name of the compound. So you must first of all interpret the name to the structure and then start checking or assessing what all the carbons one after the other. This guy is not a chiral carbon. This guy is not a chiral carbon. This guy is not a chiral carbon. However, there is a chiral carbon here because this guy has 4 different attachments. OH is not the same thing as CH3. CH3 is not the same thing as H, and this is not the same thing as this. So this guy has 4 different attachments. So because of this, this molecule is a chiral molecule. And this molecule is also known as optical isomers. Right? Okay. Now, let's look at another point. Please note, go down. Note chiral molecules or optical isomers are optically active. They are optically active. What does it mean for a compound to be optically active? Optically active means that they are able to rotate plane or polarized light. So somebody asks, just imagine somebody asks and say, what does it mean for a chiral molecule to be optically active? It's very simple. For something to be optically active means that it has effect on light, not just anyhow light, plane polarized light. If a plane polarized light is actually channeled into a chiral compound, that young man is going to change the direction of the light, thereby rotating that light. So the first point is that a chiral optical isomerism, right, is exhibited by compounds that rotate plane polarized light. And I say compounds that exhibit optical isomerism are called chiral molecules. Is it not so? From chiral molecule, I went ahead to say what is a criteria that a compound must possess to be able to be called a chiral molecule. We say the presence of a what? A chiral carbon. A chiral carbon is also known as what? As metric carbon. And what is a chiral carbon? Carbon with how many substrates? Same or different? Different. All right. We have these 3 examples. We have 2-butanol, 2-phenyl, 2-propanol. We have 2-hydroxy propanoic acid. Now, these 3 examples here is actually under chiral molecules. I'm taking this one after the other so that you see the different ways question will be asked. All right. So we have 3 questions here on that chiral molecule, and the question says, which of the following is a chiral molecules? Now this is an exam question. If you check your past questions, you're going to see this, so that you don't just be reading your textbook and then you're expecting that they only ask you an answer. And look, at the end of this class, we definitely must have exhausted all the possible ways questions will be asked. Now, the first thing first, we know what a chiral molecule is. For a compound to be called a chiral molecule, you just need one thing to be present, a chiral carbon. Is it also? Now, when we get to meso compound, we're going to see another type of compounds that contains chiral carbon but are not optically active. Class, first thing first, let's draw these structures because you cannot tell if this guy contains a chiral carbon. So the first one, to say 2-butanol. Butanol means how many carbon? 4. All means there is OH, right? As carbon 1. Carbon 2, sorry. So this becomes 1, 2, 3, and 4. 4 carbon, right? So I come here, I put OH. This is carbon 1, 2, 3, and what? 4. On carbon 2, there is OH also. So I put this here. So this becomes CH3. Here is H. This is CH2. And this guy is downward. Now, so let's assess this guy to check if there is one chiral carbon in this compound. One or more. Now, let's label the carbon atoms present here. Carbon A, B, C, and D. Class, don't always be in a haste to jump to the center carbon. No, make sure you assess all the carbon one after the other. Carbon A is not a chiral carbon because carbon A has 3 same type of substituent. That's hydrogen also. This guy is not a chiral carbon. Carbon C is not a chiral carbon because carbon C has 2 same type of hydrogen or substituent. Carbon D is not. However, look at carbon B. This as a whole is seen as one substituent. Ethyl. Ethyl is different from hydrogen, right? Hydrogen is different from what? Ethyl. And it's different from hydroxy. So realize that carbon B is a chiral carbon, is it also? So therefore, this guy is a chiral molecule. That's the first one. This is a chiral molecule. Now let's look at the next guy. So the first one says propanol. This is the parent's name, right? We actually interpret the name of the compound starting from the parent's name. Propanol is 3 carbon, is it also? 3 carbon, but this all means that the OH is a carbon number what? 2. So we have 1, 2, and 3. This is carbon 2. At carbon 2 we have all. At carbon 2 we still have what we call phenyl. Phenyl is benzene ring that have lost 1 hydrogen. So you have to C6 what? It's fine, that's phenyl. Now you put what here? CH3 and what? Is there a chiral carbon here? There is no chiral carbon there. Are you sure? Alright, hold on. There's no this guy. Benzene ring does not have the chiral carbon as a whole. CH3 is not a chiral. This guy is not a chiral carbon because 3 substituents are attached to this. So also, this guy is not a chiral carbon. This guy looks like a chiral carbon. Looks like, but it's not. Because this and this are the same. So we say that a chiral carbon must have 4 different types of substituents. So because it has 2 same type of methyl, this has neutralized this guy as a chiral molecule. So this is not a chiral molecule. You need to be very, very careful. Okay, so let's look at the last guy. Okay, so we have the parent chain here is what? Propanoic acid. Propanoic acid means that 3 carbon atanoic acid. So this is called propanoic. Pro is 3. 1, 2, and 3. Oic acid means that carbon 1 is COOH also. So this is O4H. Now at carbon 2, we have what? Hydroxy is OH also. Now if you complete this guy, this is CH3 and this H. Is there a chiral carbon here? Is there a chiral carbon here? This guy is a chiral carbon. But this guy is attached to 1, 2, 3, and 1. And 4 of them are not the same. So this guy is a chiral carbon. So therefore the question says, which of the following is a chiral carbon? The answer is the first one, which is 2-butanol, and This guy. So the answer is number 1 and number what? 3. That is it. Please let me stop the video. Look at right. Yes, look. We want to look at enantiomers, right? We are done with chiral molecules, how you can identify which compounds are chiral molecule in a set of other compounds. Now, since we've actually gotten that point, another important point we like to look out for is enantiomers. Class, what are enantiomers? Please write down. Enantiomers are pair of chiral molecules. They are pairs of chiral molecules that are mirror image of each other. They are pair of chiral molecules that are mirror image of each other. They are pair of chiral molecules that are mirror image of each other. Pairs of chiral molecules that are mirror image of each other. Now, anytime you hear of enantiomer, one thing to come to your mind. Enantiomer refers to as two compounds, right? Each of them, they are mirror image of each other. Your right hand side, the mirror of your right hand side is your what? Left hand side. So imagine, for example, now if you combine your two hands together, these are pair back. So that is actually what we mean by enantiomer. So first and foremost, you need to choose a chiral molecule. First, take the mirror image of that chiral molecule, combine both of them together to form the word enantiomer. Now this is what I mean. Example of enantiomer. First, we have CH3, COH, H, N. Plus, this carbon is a chiral carbon. And because this guy is a chiral carbon, this molecule is a chiral molecule. Do you understand? This molecule is a what? Now, if I put a mirror here, class, how do I get the mirror image of a compound? The mirror image of a compound is simply by flipping the sides. Flipping the what? What was initially on the right hand side goes to the what? What was on the left goes to the what? Up and down remains exactly the same, no change. So the mirror of this guy will be C, my mirror on my carbon. Right hand side was OH, you know, so this guy will now come to the what? Left hand side. This guy now come here. Now this becomes F and this becomes what? H. Now these two molecules are what we call enantiomers. A pair of chiral molecules. This guy is chiral because it possesses a chiral carbon. This guy is also chiral because it possesses a chiral carbon. Now, what is the relationship between these two compounds? They are mirror what? Image. Apart from their sides, the up and down remains exactly what? So these two compounds is called what? Enantiomer. Alright. Alright, so let's come back to this. I said that enantiomers are pairs of chiral molecules that are mirror image of each other. So anytime we talk about enantiomers, we're referring to two compounds in one. Okay? Now we say the one that rotates, remember, both compounds they are actually optically active. And if something is optically active, it means that it can rotate plane of polarized light. Now, out of those two compounds, the one that rotates to the right is called dextro rotation and has the symbol of what? Plus. Now, the one that rotates to the left is what? Called what? Level rotation. Has the symbol of what? Minus. Now, there's an important part I would like us to take note. Now, in absolute configuration, the R and the S. Right? Now, if one of the enantiomer has absolute configuration of R, the other guy must have what? S. Because S is the opposite of what? R. It means that since we are mirror image, if I'm going to the right, obviously the other guy is going to the what? Left. So if I'm R, you have to be S. If I'm plus, you have to what? Minus. Okay. Does anybody pass question here? Now let's start racemic mixture, right? Let's start racemic mixture. Now, what is a racemic mixture? Now, please go down. This is a mixture. This is a mixture of an equal amount equal amounts of a pair of enantiomer. Equal amounts of a pair of enantiomer. All right, so we said that the racemic mixture is a mixture of equal amounts of enantiomer. Now, what do I mean? For example, if I have, this compound OH, H, CH3, and N. And then I put a mirror image here. CH3, C, and N. Now this is it. Now this is a mirror image of this guy. So if I have this two compound here, let's say for example, I mix this guy. Let's say this guy is a R because in a dance room, one of them must always have R, and the other guy must have what? N. So let's say this guy is R, obviously this guy will what? Nice. If I bring 50% of R and mix it with 50% of what? Nice. This guy will form a resting mixture. Right? Because a resting mixture is a mixture of equal what? Amounts. If I say 55, 45, 45. Is this equal amount? No, this is not a racemic mixture. If I mix what 55 and 45, it's not a racemic mixture. Right? But if I have 50 and 50, that's the what? A racemic mixture. So in case you're being asked, they will not ask you to draw the structure. They'll ask you a mixture of equal amounts of enantiomer. There are two ways they can ask that question. In place of this equal amount, they can choose to use this. You can choose to use equimolar quantities. Equimolar means equal amounts. Alright? So once you mix two compounds and a mirror image of each other in equal amounts, that forms a racemic mixture. Okay, what are the features of a racemic mixture? Racemic mixture are optically inactive. They are optically inactive by external compensation. They are optically inactive by external compensation. All right. Now these are features of chiral molecule. Now, why did I have to give all these features? It's very, very important so that just in case the exams, they ask us. Now, please take note that all chiral molecule lacks plane of symmetry. What does it mean for something to lack plane of symmetry? You cannot divide the compound into two halves. Right? No matter how you want to try, you can't divide it into two equal halves. You can divide it into two, but both of them can never be the same thing. That really means for something to lack plane of symmetry. That means you cannot share it into two equal halves. Now this guy says chiral molecule and its mirror image are called enantiomers. Of course, we know that part already. Now this other part says chiral molecules cannot be superimposed on their mirror image. They cannot be superimposed on their mirror image. What does it mean for something to be superimposed? Now, if you place your hand as if you're clapping, I'll give you a typical example. If you put your hand like this, right? You've superimposed the left hand side on the right hand side. Anybody that is doing it from this direction is not going to see 10 fingers. It's going to see how many? 5. right? That's the meaning of superimposable, right? You superimpose this guy on this. When you place your hand as if you're banging, obviously, if I look at it from this, I'll know that it's 10 fingers, right? So, chiral molecules cannot be superimposed on its mirror image. That means, remember the example I gave us earlier, right? Imagine you have two compounds, that two compounds I gave us. Imagine pulling out one to place it on the next one. The up and the down can actually superimpose because mirror image up and down are always the same, it's not so. But the sides can never superimpose because the sides are what? Opposites. Alright? So that's what we mean by they cannot be superimposed on their mirror image. Okay, now just as we have chiral molecules class, we also have what we call achiral. Opposite of chiral is what? Achiral. Take note of that. Right? Achiral simply stands for opposite of everything here. Chiral molecule has chiral carbon. Some achiral molecule does not have what? Chiral carbon. Chiral molecules are optically active. Achiral molecules are optically inactive. Take note of that. Chiral molecule lacks state of symmetry. Achiral does what? Has. So achiral is spelled as ACHI. Achiral is directly opposite of what chiral stands for. Achiral, chiral molecule and its mirror image are called enantiomer. There's nothing like enantiomer with a chiral molecule. Because for any compounds we call enantiomer, first it must be what? Chiral. Now when you now take a mirror image of the chiral, you now form a pair, you should also. So a chiral molecule cannot form enantiomer. Do you know why? Because this guy is not optically what? Active. So that's why chiral molecules cannot be superimposed on their mirror image. Whereas a chiral molecule can be what? Superimposed. So I won't want to start going into detail about a chiral. Just know that a chiral molecule is the opposite of chiral. Now, what is the example of a chiral molecule? Now, sorry, let me just give us two examples or two instances where we can say a chiral molecule. Then, number one, example of a chiral molecule. Number one, molecules or compounds that does not have a chiral carbon. Any compound that does not have a chiral carbon is considered a chiral. So you can draw any compound at all as long as that guy does not have a chiral carbon, that guy is considered a chiral. Now, what is the second example of chiral molecule? A chiral molecule. Compounds with identical Now, I said two compounds can be called a chiral. The first one is that any compound that you can think of that does not have any chiral carbon, obviously that compound is a chiral. Point number one. Point number two is any compound that contains identical two or more chiral carbon. In this case now, it has chiral carbon, but not one. All compounds with one chiral carbon are chiral. But once a compound has two chiral carbon, you need to be very, very careful because there are compounds that, although they have two chiral carbons, they are not chiral. So example of compounds that have two or more identical chiral carbons are chiral. What do we mean two or more identical chiral carbon? I'll tell you. But that type of compound is called what? That. Somebody asks, what is a meso compound? Meso compound is a compound that contains two identical chiral carbons. Now, let me give you an example of the meso compound so that you understand what I mean by this. So, in case we have CH3 plus stop. This is a pure case of a meso compound. This carbon here, the one with asterisk, is chiral. Now, how are they identical? I'll show. Now, let's consider this carbon. The right hand side of this carbon has OH also. Now, let's consider this other chiral carbon. The right hand side has what? OH. So, on both sides, these two guys have same type of substrate also. Look at the left hand side. Left hand side has H. This guy has H. Also, this is identical. Look at the up. Up has CH3. Up has what? Down has CH3. So this is an example of a compound with two chiral carbons, but is considered achiral. It's considered what? This compound is optically inactive. So somebody asks you, why is it that meso compounds are considered a chiral molecule? Is because they contain two identical what? Chiral carbons. And these two chiral carbons, listen, please stop right now, look up. The reason why meso compounds are optically inactive is because it actually contains plane of symmetry. Remember, chiral molecule lacks plane of symmetry, right? What do you mean by contains plane of symmetry? Class, if I put a mirror here, do you know that I can divide this guy into two equal halves? Let me tell you, if you put a mirror here, I'm only going to be seeing one OH. I'll see only one. This will superimpose on this. There are two OH here, but if you put a mirror here, you only see how many OH. One. This will also superimpose on this, and this will superimpose on this. So chiral meso compounds are considered achiral. Number one, they have plane of symmetry. Number two, they are superimposable on their mirror image. They are what? So it's an example of a meso compound. So meso compounds are achiral, right? Take note of this point in case you are being asked in exams. So let me also state this here. Meso compounds are optically inactive. By internal compensation. So that is it. So we're going to run to the past question to see how we can answer some few questions. Is there missed something? Combination of optical isomers, which is also known as stereoisomers. Now, remember I told us that if a compound should have one chiral carbon, or perhaps I did not tell us, let me tell us now. If a compound should have one chiral carbon, that guy can only have one mirror image, right? So that the mirror image and itself will not give us how many compounds? Two. So if you want to solve number of optical isomers, you use this formula 2 raised to 4 of n, where n is the number of chiral carbons. So if you're asked to find the number of optical isomers that is present in a compound, all you just need to do, check the number of chiral carbon that is present in that compound, right? And then insert it here. So look at this question. They say a novel syntax. What does it mean for something to be novel? New, the very first time. A novel syntactic compound has 3 different chiral carbons. How many optical isomers will possible? Now the answer to that question is 2 raised to 4 of n. Our n here is number of chiral carbon, which is how many? 3. So this becomes 2 raised to 4 of what? 3. Which is equal to how many? So this guy is going to have 8 optical isomers. Alright? Now, how many isomers exist for a compound with 4 asymmetric carbon atoms? Class, remember that chiral carbon is also known as what? As mentioned. So this is going to be 2 raised to the power of n. Our n in this case is how many class? 4. So this is 2 raised to the power of 4. That's equals how many? 16. So that's how we're going to solve this to get the answer.